Okay, so I think we can get started. Um, so last time I think we were talking about like the determinant of a number, like in algebra, in a typical algebra course, you are probably being told that a number A has a multiplicative inverse if there exists a number B. A number A has a multiplicative inverse if there exists a number B such that A times B is equal to 1. So in this particular case, in order for us to have a 1, we should have another number 1 over A such that uh, 1 over A is different from 0. Sorry about that. That number 1 over A uh, is the number associated with this number A such that the product will give us the matrix 1, and at the same time at the same time, if a here is equal to 0, this expression, this multiplicative inverse, does not exist. So if we consider a one by one matrix, A being a one by one matrix with entries in the first row 1 and the first column, so A would have a multiplicative inverse if and only if A is not equal to 0, because so A will have A is not equal to 0. So that number that fulfills such condition is what it um, will be. So the number that is fulfilling such condition for a matrix is what we call the determinant of the matrix A. So that determinant of the matrix A should not be equal to 0. And in this particular case, the determinant of A is going to be A, and that A should not be equal to 0. So A is non-singular. Non-singular are abbreviated with non-ns. N is non-singular. A matrix A is non-singular if and only if its determinant is not equal to 0. We can move further to another type of matrix. So here's like case number 1, where we have a one by one matrix. Case number 2, let's consider a second case. You have a matrix A like this one, A11 here, A12, A21, and A22. So in order for this matrix to be non-singular, it has to be row equivalent to the identity. If A is row equivalent to the identity, then it's non-singular. If the matrix A is row equivalent to the identity, then it is non-singular. So we can perform some operations on the matrix A. If we perform some operations, row operation on the matrix A, we can obtain the following: A11 0 here, A12, A11, A22, minus A21, and then A12. So this matrix will be equivalent to the identity if and only if this part is not equal to 0. So this matrix is rho equivalent to the identity if and only if this part over here, so 1 to 2 minus 2 1 1 2 is not equal to 0. And from this matrix, for this matrix A, for this 2 by 2 matrix, we can define the determinant of that matrix A as this value over here. Now let us consider another case, a 3 by 3 matrix. But before we even move on, let us say something. So if you have like a matrix A like this, 3 2 4 1, that matrix A can be, this is like a matrix notation. You can write determinant of A like this, or to write determinant of A, you write it this way. That's another notation for the determinant of the matrix A. Like the 3 by 3 case will also lead us to find a certain determinant. Let's say you have a matrix A like this, and case number 3, a 3 by 3 matrix. So you have a 3 by 3 matrix with entries A11, A21, A31, A12, A22, A33, A32, A13, A23. Now, if you were to find a matrix that is very equivalent to this, no, if you want to find a matrix, like the matrix, if you were to reduce it, you'll find another matrix. And that matrix would lead you to the following information. The determinant of the matrix A equals to this one over here, A11, A22, A33, minus A11, A32, A23, minus A12, A21, A33, plus A12, A31, A23, minus A13, A21, A32, minus A13, A31, and A22. So the matrix A will be equivalent to the identity if and only if this number over here is not equal to 0. Later on, we're going to get to how to find these numbers, but as for now, we are introducing the concept in general. So for a 3 by 3 matrix, the number that needs to be not equal to 0 for that matrix to be non-singular is this number that you obtain by this multiplication of entries, this additional multiplication of entries. So from that, we can try to generalize for further cases for for n greater than for the number of entries, for the number of rows and columns greater than 3. So here we have the case where we have 3 cases, but from here we can generalize. So let's say that I have a matrix. Before I even start to generalize, we can observe something, can make an observation. Here I notice that I have A11. Let me go down. A11 here, A11 here. So I can factor out A11. Here I notice that I have A12, A12. I can factor out A12, A13, A13. I can factor that out. So if I factor that, A11, A22, A33 minus A32, A23, and I can factor this one and that one. So here I can write minus A12 factor of A21, A33 minus A31, A23. And then I can further factor by A13, A13 factor of, because there is a negative sign here, negative sign, I can even write the negative sign in front of the expression. Okay, so I'll leave it like that. Later on, I'm gonna introduce the negative sign, but I'll leave it like this. Later on, I'll change it.
Not better
I'll
to
factor
to
out.
put minus.
A22. Okay, so now I can pull out the negative sign and bring it over here. Okay, so A13 time the last part, A21, A32 plus A31, A22. So from this formula, we can observe a certain generalization. That's the generalization that I really want to explain. Let me go here. We can notice a pattern. That's what I wanted to say. We can notice a pattern, and that's the pattern that I want to explain. So we notice that we took A11, and it as if after taking A11, we erase the first row, and we have erased the first column. And then we've copied these entries over here. So let me explain how that happened. So determinant of the matrix A. I take the entry in the first, I'm looking at the first row. My goal is to go through the first row. So I take the first row over here, the first entry in the first row, and I delete the first row, the first column, and I have this small matrix over here. So I have A11, and here I have the product this one times this one, A22 minus time A33 minus A, so it's like this, and I don't know if you can see, I delete these and this, and I'm left with this matrix over here. Okay, I'm left with this matrix over here. A2, no, okay, we cannot see, but it as if we were, let me try this way. Yes, here it is, we can see it now. Yes, so it's like you have if you take this element A11, A11 is located at the first row in the first column. So that means I have to eliminate the first row and the first column. So if I eliminate the first row and the first column, I'm left with a matrix, with this matrix over here. So if I take this one times this one minus this one times that one, I obtain the following: a, so this one times this one, and then this one minus that one, minus a, um here there's a 3, so a32 times a23. Okay, now minus, moving on to the next one, a, so I'm moving along the rows. Moving along the rows, I take this entry over here. I'm taking this entry over here, and I have to eliminate the first row and then the second column. So I eliminate the first row and the second column. So it's not seeable. First row and then second column. I'll be left with this matrix: A21, A32, A23, A33. You're gonna do the product of these, this times that minus this times that. Put it here. A12 multiplied by A21, A33 minus A23 times A31. Okay, plus, I'm now taking the third one. I'm coming, I'll explain. You will see where we are going, but be patient and then bear with what with the process. Yeah, this one, the third one here, we take this row. So that means we're looking at the entries. It says first row and then third column. So that means you have to eliminate the first row and the third column. So I eliminate the first row and then the third column. And I'm left with this small matrix here. And then I'm gonna do the multiplication by diagonal. So this one times this one minus the other multiplication by diagonal, this one times this one. So that's going to give me A13, A13 multiplied by multiplied by A21 times A32 minus A22 times A31. Okay. So that determinant of A, okay. Yeah, I think okay. So actually the determinant of A is actually this number over here. This number over here. Okay, so in a note there's a typo. There is a typo in the notes. I will fix it later on. In the note there's a typo. I'll fix it. But the main point is that the determinant of A is obtained this way. So from that you can come up with some definition. So now there is a, we can call, so like if you have like A being a matrix with entry ij like this, A is an n by n matrix. And we have a matrix, what we call a minor of a matrix. It is denoted by M, big M, capital letter M with entries ij. And that minor matrix is obtained by deleting the Mij. M sub ij is obtained by deleting, by removing the first, the row and the column by deleting the row and the column containing ij. Okay, so coming back to this example here, the minor m sub ij. Let's see that let's assume that I'm looking for m sub 1 1. It's a matrix obtained by deleting the row and the column containing the entry A11. So M11 is a matrix obtained by deleting the row and the columns of A sub 11. So let's look for A11. A11 is this matrix over here. A11. Now A11, how to delete the row is the row and the columns of M11 you have to update you have to remove the row and the column containing A11. So here I have A11, I have to remove the row that contains A11 and also the column that contains A11. Okay, 1 second. Okay, so like I was saying, I have to remove the row containing A11 and also the column containing A11. So this is like the row contained by A11 and a column containing A11. So if I remove that row and that column, I'll be left with that matrix over here. The matrix over here, and this small matrix over here. And that matrix is what we call the minor A11, M11. So let me write it down over here, M11. So the matrix M11 is is given by eliminating the first row and the first column of the uh, entry located at the 1 1 position. So I eliminate this one, I'll eliminate that one, and I'll take the matrix over here inside. So A22, A23, and A32, and then A33. Now the second matrix. So here, if I take the determinant of this matrix M11, if I take the determinant of that matrix M11, that's going to be equal to taking this row, so this one times this one, and then minus this one times this one. So that's going to be A22, A33 minus A32, A23. So we notice that, okay, this is M11. Determinant of M11 is equal to this entry, this value over here. So we can observe that the same value is being repeated over here. So the determinant of A equals to determinant of A equals to A1 multiplied by the determinant of M11, determinant of M11 minus, let me write the minus sign, A12. Now, what is that? What is that value over here? So let's look at, for example, let's look at the matrix obtained by eliminating the this the first row and the second column. That matrix that is being formed is this one with entries this, and that. So let's call that matrix M12. The matrix M12. Okay. The matrix M12 is obtained by eliminating the first row, oops, the first row, and then the second column here. So we have this matrix. So I'm gonna enter the entries. The entries that we're gonna have are this one, that one, and that one. A21, A23, A31, A33. So if we look for the determinant of M12, if we're looking for the determinant of M12, determinant of M12 is going to be the determinant of these entries. So I'm taking this diagonal, multiplying the diagonal element. So this one times this one minus this one times that one. A21, A32, 3 minus A23, A31. So we can notice that this value that we found over here is equal to this value over here. So minus sign here multiplied by the determinant of M12. And if we were to do for the third one, this matrix M3, M13 is obtained by deleting the row and the column containing A13. A13, let's try to delete the row and the column of A13. And there's a plus A13. So the matrix obtained by deleting the the row and the column of M13. This is the row, this is the column. The matrix that you obtain is this matrix over here. So I'm going to copy the entries into this matrix over here. Now, the determinant of M13 is obtained by multiplying the diagonal element minus the other diagonal element. So A21, A32 minus A31, A22. And I notice that this is the same as this value over here. So I'll copy this one is the determinant of M13. So in other words, the value that needs not be equal to 0 for the 3 by 3 matrix to exist has the following pattern. So the determinant of A is equal to A11 determinant of M11 minus A12 times the determinant of M12 plus A13 times the determinant of M13. Okay, now we can further generalize. We can define a matrix. We can define a number. That number is formed by the following. The matrix, you take the matrix, so it's like you take the determinant, you take, so A will be denoted as A sub ij, like this. And A sub ij is going to be equal to minus 1 raised to the power I plus j multiplied by the determinant of that matrix, that minor matrix, determinant of mij. So if If I am dealing with, if I'm looking for determinant of A11 like this, the entry over here is going to be negative 1 raised to the power 1 plus 1. And that's going to be A11 is going to be positive determinant of M11. Now, if I'm looking for A12, is going to be equal to negative 1 raised to the power 1 plus 2, which is 3. And the determinant of M12. If I'm looking for A13, it's going to be negative 1 raised to the power 1 plus 3, determinant of M13, like this. Okay, I haven't finished this one, by the way. I'll come back to this one. So the A12 is going to be negative 1 raised to the cube. And negative 1 cube is just negative 1. So negative 1, uh, negative 1 and the determinants of M12. The next one is this one, A13 is equal to negative 1 raised to the power 1 plus 3, determinant of M13. And that's going to be a positive number because the power is to the power 4. So I get determinant of M13. So here is what I can notice. I can notice something else. This one over here, determinant of M11, can be replaced by A11 like this. This value here, A11, the formula over here, the value here is what we call the cofactor. So instead of writing in terms of minor matrices, I can write it in terms of factor, the determinant of A, in terms of cofactors of the matrix A. So the cofactor, in terms of cofactors, I know that determinant of M11 is equal to A11, so I'll replace this one by A11. Now, the second one, A12. A12, I can see that there is a negative sign here, and the negative sign goes to determinant of M12. So here there is a negative sign going to determinant of M12. So I can rewrite it as plus A12 multiplied by negative determinant of M12. Okay, I'll come back to that, plus A13. A13 times determinant uh, M13. Determinant of M13 is A13. A13. I'm coming back to the last one over here. A11 plus A12. Here, negative determinant of M12. That the negative determinant of M12 is actually A12. A12 plus A13, A13 like this. So for a given matrix A, we can write that matrix as the sum of cofactors expression, or we can write it as a sum of cofactor expression, the determinant of a matrix. So we can generalize. You can even go further to here. We have three entries. We can use that principle to go for a 4 by 4 matrix. So given a 4 by 4 matrix, for instance, if you're looking for a determinant of a matrix A that is 4 by 4, you can do this. A12, A12 plus A13, A13 plus A14, A14 times A14 like this. And from there, you can break it down. Coming back to a 3 by 3 case, this was a 4 by 4 case. But coming back to a 3 by 3 case, the determinant of a matrix A in terms of cofactor expansion is as follows. Here we move along a row. Here we move along this row. We've used this row. It's like we fix this row. We are moving along this row. But we could have moved along the second row. We could have moved along the third row, or we could have moved around the columns to create our M11, etc. So for a 3 by 3 case, we have this matrix as this one. So if you were to calculate the determinant of that matrix, you take A11 multiplied by A11 multiplied by negative 1 raised to the power 1 plus 1, determinant of the minor matrix formed by deleting the first row and the first column, plus A11 negative 1 raised to 1 plus 2, determinant of the matrix formed by deleting the first row and the second column, plus A13 multiplied by negative 1 raised to the power I plus j 1 plus 3 raised to the power times the determinant of the matrix formed by deleting the first row and the third column. And from there, you have your matrix A11. You take the A11 entry, negative 1 raised to the power 2, which is positive 1. You calculate the determinant of this matrix. Second matrix here, you can see that is raised to the power 3, becomes a negative number. That one is a negative number. And then you look for the determinant of this entry over here, plus this one. This one is going to be negative 1 raised to the power 3, becomes 4. And then for negative 1 raised to the fourth power is positive 1. So here you have 1, 3. And then you take the determinant of this matrix formed by these. Okay, so that's how you calculate. Like this is like the general form. But if we see an example, it will make sense. Let's say that I have a matrix like this, a small matrix 2, 3, 4, 1, and you want to calculate the determinant of that matrix A. You take, in other words, you're looking for this. All I have to do is just to do the multiplication of the diagonal element and then subtract. So this one times that one minus this one times this one. So that's going to be 2 times 1 minus 3 times 4. And that's going to be equal to 2 minus 12. And that's going to be negative 10. That's for a 2 by 2 case. You simply write it this way and then you solve. What if you were given a 3 by 3 case? Let's move on to the 3 by 3 case. So determinant of a matrix A, and that matrix A is as follows. 2, 3, 5, 5, 1, 4, 2, no 4, 2, and then 6. You want to find the determinant of that matrix. You can use the formula that is dealing with cofactors expansion. You have determinant of A. You will start with the first entry. Let's assume that I want to fix this row here, move along this row over here. I want to move along this row. So the first entry of that row is A11. The second entry is A12, this one, and the third entry is A13. And now I need the cofactors, so A11. So the cofactor associated with the first entry over here is A11. The cofactor associated with this entry over here is A12. And the cofactor associated with this one over here is A13. Like I said, I'm moving along this row. I could have moved around the second row. I'll have the same result in the end. I could have moved along the third row. I'll have the same result in the end. I could have moved along the first column. I will have had the same result in the end, etc. So if I use this formula over here, this is what I get. A11, A11 is this entry over here. Um, Before I even turn it into into numbers, let me try first to return it in terms of minor expression. If you remember, if you have a I j, that's going to be equal to negative 1 I plus j multiplied by the determinant of the minor matrix that's formed by deleting the if row and then the jf column. So let me transform that cofactor into this A11, and that's going to be negative 1 raised to the power I plus j. I here is 1, j is 1, so 1 plus 1. Determinant of m ij 1 1 plus A12 multiplied by negative 1 raised to the power 1 plus 2, 1 plus 2, determinant of M, the matrix formed by deleting the first row and the second column, and then plus finally A13 multiplied by negative 1 raised to the power 1 plus 3, 1 plus 3, and then multiplied by the determinant of M13 like this. So here A11 negative 1 square is just positive 1. So multiply by determinant of this one plus, so here there is a negative sign, cubed. 1 cubed is just negative 1. So the negative 1 will be, I'll move it here to the plus sign. So negative here, negative this entry, the first row, the entry located at the first row, second column, multiplied by the determinant of M12. And then finally, this one over here, you can see that negative 1 raised to the power 1 plus 3 is 4. So that's going to be positive 1. So A13 multiplied by positive 1 is just A13. So plus A13 determinant of M13. So A11, now we'll turn these into numbers. A11 is the entry located at the first row, first column, so that's 2. Determinant of M11 is determinant formed by deleting the first row and the first column. So this one and that one are eliminated. First row, first column. This one is eliminated. This one is eliminated. So all I have is this one over here. The determinant of this matrix 1, 2, 4, 6. I copy the minus sign over here. I copy the entry located at the first row, second column, first row, second column. So I have this matrix formed. So 5 here, formed using 3, 2, 4, 5, 6, 3, 2, 5, 6. Plus finally, the last one, 4, A13. Determinant of deleting first row, no, third, third column, first row, third column here, first row, first row, and the matrix formed is this matrix over here, 3, 1, 5, 4. Now the determinant of this one, 2 times 1 times 6 minus the determinant of 2 times 4 minus 5 multiplied by this times this, 3 times 6 minus 5 times 2, 5 times 2 plus 4 3 times 12, 3 times 4 is 12, minus 5 times 1, 5 times 1. And then you start to solve 6 minus 8 minus 5, 18 minus 10 plus 4, 12 minus 5. So 2 times negative 2 minus 5 times negative 8 times 8 plus 4 times 7. And that's going to be negative 4, negative 40 plus 28. And finally, that's going to be negative 16. So if you're looking for the determinant of that matrix, you get negative 16. Now, this is a way of using the formula. It's like if you wanted to apply the formula and you want to go step by step, this is how you will do it. Another way is to simply looking at, so this is the answer. The determinant of that matrix is this. Is to simply look at the matrix A like this instead of writing all of that. You look at your matrix A. You fix this entry. You start with the rows. You are moving along the rows, the first row. You suppose that you move along the first row. You take the first entry. You take the first entry. You take 2, for example, and then you hide. You delete the first row, the second column, the first column. You delete this. The matrix inside. You write it here. Now, like if you're okay, and then you write it here. Now moving to the next one, you make it negative. The next value, so it's like you go positive, negative, positive, negative. That's how you think about it. It's like a way of doing it without formula. You go to the second. You are moving along the rows. So you are done with the first entry. Move to the second entry. Now, if you move to the second entry to change the sign, here you have a positive sign when you started. Now it becomes negative sign. Now for the negative sign, you take the entry 5, and then you delete, uh, you delete this column, and then you delete this row, and then this row over here. And you obtain 3526, and you copy 3526, 3526. Now it's like you go plus minus plus. So here the next one is plus. You don't think too much. You look at 4 here, you take the 4, and then you eliminate everything else. You take that matrix here, take the determinant of that. So that's going to be 3, 1, 5, 4. And then that's over. You do 6 minus 8, 18 minus 10, 12 minus 5. That's going to be negative 2. That's going to be 8. That's going to be 7. And that's going to be negative 4, negative 40. That's 28. And that's going to be negative 7. Okay. So you can do it 2 ways. One way is to have like the formula, the regular normal formula. The other way is to compute by like algorithm of computing. You start with your first row, you don't think too much. Start with your first row, and then you assign the following. The first the first value, the first term that you're gonna have will have a plus sign. The next term a negative sign. The third one a positive one, etc. And then you take the first entry, and then you delete the rows and the columns. You have your determinant, delete rows and column determinant, etc. So in this way, you don't think too much. Just apply the way of calculating. But here, you're actually using the formula, the official formula, to find the answer. So any questions related to this one? Okay, so if not, let's go to the notes. So section 2.1, the determinant of a matrix. With each n by n matrix, it's possible to associate a scalar determinant of A whose values will tell us whether the matrix is non-singular. Let's take a look at on three cases before generalizing. Case 1, one by one matrices. If A is equal to a matrix entry A is a one by one matrix, then A will have a multiplicative inverse if and only if A is not equal to 0. Thus, we define the determinant of A. Then A will be non-singular if and only if determinant of A is not equal to 0. Now, case number two, two by two matrices. Let A equals to this matrix. By theorem 1.5152, A will be non-singular if and only if it's row equivalent to the identity. By performing reduce operations to the matrix A becomes the following. This matrix over here. The matrix is row equivalent to the identity if and only if this value over here is not equal to 0. Thus, if A is a 2 by 2 is any 2 by 2 matrix, we define the determinant of A as being this number over here. Then A is non-singular if and only if the determinant of A is not equal to 0. Next notation, we can refer to the determinant of a specific matrix by enclosing the array between vertical lines. So example of that, A is equal to the matrix 3, 4, 2, 1. Then the vertical lines inside, like the matrix, instead of the matrix symbol, you put vertical lines, represent the determinant of A. We can also use determinant of A to mean the determinant of A. Um, Now, case 3, 3 by 3 matrices. If we proceed in a similar fashion as in case 2, we'll find that for a 3 by 3 matrix A, with these entries, the determinant of A will be equal to all of these. Now you can also write determinant of A as in terms of factors. So you have A11 here, A11 here. So you factor these values and you obtain this value over here. Now for j going from 1 to 3, let m sub some 1j denote the 2 by 2 matrix block matrix formed from A by deleting its first row and jf column. The determinant of A can be represented as the following. Determinant of A equals to A11 determinant of M11 minus A12 determinant of A12 plus A13 times determinant of M13, where M sub 11 is equal to this matrix over here, M sub 12 is equal to this other matrix, and M sub 13 is equal to this other matrix. Now let's generalize for n greater than 3. Definition. Let A be a matrix with ij entry. A is a m by n matrix, and let m sub ij denote a n minus 1 time n by n minus 1 matrix obtained from A by deleting the row and the column containing A sub ij, the entry A sub ij. The determinant of m sub ij is called the minor of the ijth entry. We denote the cofactor A sub ij of A sub ij by A sub ij equals to negative 1 raised to the power I plus j multiplied by the determinant of the matrix M sub ij. So for a 2 by 2 matrix A, we write the determinant of A equals to this expression. And A sub 1 1 multiplied by the determinant of M sub 1 1 minus A sub 1 2 times the determinant of M sub 1 2 in the form, this form. So for a 2 by 2, if you wanted to write it in terms of cofactor expression, this is what we have. Determinant of A11, A11 plus A12, A12. This new form with the cofactor is called the cofactor expansion of the determinant along the first row of A. We could have found the determinant of A by deleting the second row instead of the first row. We'll have obtained the following. Determinant of A equals to this expression. That is equal to that expression over here. This new expression represents the determinant of A in terms of the entries of the second row of A and their cofactors. So as you can see here, they started elimination in the second row, and your result is going to be the same as if you're going along the first row. So I think this is the example that we have just done. Okay, so let's move on to the next example, to the next one, the next page. Okay, so now here we'll see related to some more definitions related to cofactors and the other formula. So the determinant of a 4 by 4 matrix can be defined in terms of cofactor expansions along any row or column. So let's go with a definition, a very powerful definition. Definition: the determinant of a m by n matrix, denoted as determinant of A, is a scalar associated with the matrix A that is defined inductively as the determinant of A will be equal to the entry A sub 1 1 if you are dealing with a n by 1 matrix, if n equals to 1. Now, if n is greater than 1, if you're not dealing with a 1 by 1 matrix, um, the determinant of A is going to be equal to, so you fix the row, like let's say you fix row 1, and then you are moving it along the columns. So you have A sub 1 1 A 1 1 plus A sub 1 2 A 1 2 plus dot 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 A sub 1 n A sub 1 n, or n greater than 1, where A sub 1j is equal to negative 1 1 plus j multiplied by the determinant of m sub 1j. J goes from 1 to n, and these are called the cofactors associated with the entries in the first row of A. Okay, so A sub 1j is the cofactors of the matrix A associated with its first row. So questions related to this one? Okay, so it's not necessary to limit ourselves to using the first row for the cofactor expansion. So here's a theorem. So if A is an n by n matrix with n greater than or equal to 2, then the determinant of A can be expressed as a cofactor expansion using any row or column of A. So the determinant of A, here's the first case and here's the second case. If you're using columns, if you're using rows, you are fixing one row. Let's say you fix row I, can be row 1, and then you move along the columns. If you are fixing a column, you can, like, you have entry A sub 1j. What is changing is your rows. So you fix the columns, you take, let's say, row column 1, and then you move your values along the rows. So this is the formula for that. I goes from 1 to n and j goes from 1 to n. If A is a n by n matrix, the determinant of A transpose is equal to the determinant of A. Theorem 213. If A is a n by n triangular matrix, then the determinant of A equals to the product of a diagonal element. So if I have like a triangular matrix, it can be upper triangular, lower triangular. Uh, the way to find the determinant is just do the product of the diagonal, and that's it. I think we'll see an example of that. Now, theorem 214. Let A be an n by n matrix. If A has a row has a row or column consisting entirely of zeros, then the determinant of A is equal to 0. If A has two identical rows or two identical columns, then the determinant of A is also equal to 0. Okay, let's see examples of that. If I write something like, if I write, what's the determinant of the matrix A? Okay, no, I'm going to use another example. Um, let me use another example. That's not what I wanted to use. Okay, so what's the determinant of the matrix A without calculation? What would you say? Okay, one, two, three, four, five, six.
Zero,
Yes,
sir.
0. Because it has two identical rows and two identical columns. Okay, so the determinant of that is 0. Rows are identical, columns are identical. The theorem is saying that if you have a matrix A with two identical rows and two identical columns, then the determinant is going to be equal to 0. Okay, let's suppose, for example, you have a matrix like this one. And they ask you to find the determinant of the matrix A. So what would you like? How would you find like what would be the determinant of the matrix A? Who can guess it?
Sir,
You said
it
5?
will be 5 times 1 times 2.
Yes, that's correct. Here we are dealing with a triangular matrix. That's correct. We are dealing with a triangular matrix like this. Now, if you are dealing with a triangular matrix, find the determinant of the matrix A through the product of the diagonal elements. So 1 times 5 times 2, that's going to be 10. That's it. You don't have to do all the calculation, all of that. In 30 seconds, you are finished. Okay. So the next one is this one over here. So let's see some more properties of determinants. We're going to talk about the effects of elementary matrices on determinants. But before we do that, there is a lemma that we have to learn about. Let A be n by n matrix if A sub jk, the cofactor of A sub jk for k going from 1 to n, then we have the following. If I equals to j, we have the determinant of A. Now we have A sub I, I A sub If I equals to j, we have this equals to the determinant of a, and if I is not equals to j, this one is going to give you 0. So like I equals to j here, it means that here you have a11. If you have a11 here, you have a11, a12, a12 here, etc. So in order for this to give you the determinant of a, I and j here has to be the same. So now let us consider the effect of the three row operations on the value of the determinant. In summation, if E is an elementary matrix, then the determinant of E times A is equal to the determinant of E multiplied by the determinant of A, where the determinant of E, the elementary matrix, is going to be equal to -1 if that is a matrix of type 1, and it's going to be equal to negative, it's going to be equal to alpha if we are dealing with a matrix of type 2, and it's going to be equal to the going to be equal to 1 if we are dealing with a matrix of type 3. Now, this one, type 1, is when we are interchanging the rows. For example, you take the identity matrix and then you interchange the row. That's when you have type 1 elementary matrix. Type 2 elementary matrix when you scale by non-zero constant alpha. You take alpha being a non-zero constant and then you scale your matrix. Now, if you calculate the determinant of that, you have alpha. Of that elementary matrix, you have alpha. Now, if you have a type 3 matrix, it's a type of matrix, it's a type of elementary matrix obtained by taking the identity and you multiply one row and add it to another row. So you take the multiple of one row and then you add it to another row. In that case, the determinant of that elementary matrix is going to be 1. So similar result holds for column operations. Indeed, if E is an elementary matrix, then E transpose is also an elementary matrix, and determinant of A times E is equal to the determinant of A E transpose. That's equal to the determinant of A transpose A transpose. That's equal to the determinant of E transpose multiplied by determinant of A transpose, and that's going to be equal to the determinant of E multiplied by the determinant of A. Thus, the effect of row and column operations have on the value of the determinant, like the effect that row and or column operations have on the value of the determinant can be summarized as follows. 1. Interchanging two rows or two columns of a matrix change the sign of the determinant. Second, multiplying a single row or column of a matrix by a scalar has the effect of multiplying the value of the determinant by that scalar. The third condition, the third operations, adding a multiple of one row or column to another does not change the value of the determinant. So these are the properties that you obtain by the elementary row operation. Theorem. If A is a n by n matrix, A is singular if and only if its determinant equals to 0. Theorem 223. If A and B are n by n matrices, determinant of AB of the product AB is going to be the determinant of A multiplied by the determinant of B. The next one is another method for calculating a determinant. Okay, I think here what we have to do is just to we have to do one row operation on it. So let's read it together. So we can obtain a method for computing the determinant. Reduce A to a row echelon form. So you take your matrix A, you transform it into a row echelon form. You obtain an upper triangular matrix, and that upper triangular matrix is equal to the product of A and A multiplied by a couple of elementary row operations. So U is in row echelon form and E sub I are the elementary matrices. If A is singular, then the determinant of U, the upper triangular matrix that you obtain after doing the row reduction of the matrix A. If A is singular, that determinant of U is going to be equal to 0. But if A is non-singular, the upper U is upper triangular with ones along the diagonal, and hence the determinant of U of that upper triangular matrix is equal to 1. If the last row of U consists entirely of zeros, A is singular and the determinant of A equals to 0. Otherwise, A is non-singular. And if you find the inverse, if you try to find the inverse of A, you'll obtain that A equals to the product of the inverse of the elementary matrices multiplied by the upper triangular matrix. So with that being said, we can find the determinant of A. The determinant of A is going to be equal to the determinant of all of these elementary uh, matrices, elementary operation, the inverse of these, multiplied by the determinant of the upper triangular matrix. And we know that the determinant of the upper triangular matrix is equal to 1 based on this information over here. So the determinant of A is going to be equal to the determinant of these elementary operations when we take their inverse. Actually, if A is non-singular, it's simpler to reduce A to a triangular form. This can be done using only the row operation 1 and 3. Thus, if you have like the triangular form, so T here stands for triangular form, will be equal to the matrix A obtained from a set of row operation E1, no, obtained by a set of multiplication of elementary operations E1, E2, all the way to En. Hence, the determinant of A is going to be equal to plus or minus the determinant of the matrix T that is here. T is formed by set of row operations. So it's going to be plus or minus determinant of T. And you have like these different entries where Ti, so plus or minus T sub 1, 1, T sub 2, 2, all the way to T sub Nn. So this is like the product of the diagonal entries, where T sub ii's are the diagonal entries of the matrix T. Now the sign will be positive if row operation has been used an even number of times and negative otherwise. So you pay attention to row operation 1. You observe how many times you use it when you do your calculation. If you use it more than once, that means if you're using it an even number of time, you are dealing with you have to put the sign positive and negative otherwise. I think we can do that example real quick. That last example real quick, and then we'll stop. Okay, actually, we'll do it next time. Its time is already up, so we have to stop. We're gonna do it next time. So, any questions related to this? Okay, so I'm gonna take attendance. Okay, hold on 1 second. Okay, so Aka Cyril.
Yes, I'm present.
Okay,
Present, sir.
Apo. Okay, Aleppo Linda.
Present, sir.
Ibali Ili.
Present, sir.
Ile. Mr. Ile. Ile. Okay. Fufana Aishatu.
Present, sir.
Kahwa Hassan.
Present, sir.
All right. Lai. Mr. Lai. Okay, I'm not seeing, hearing. Merlik. This one.
Present, sir.
Ouattara Idris. Ouattara Idris. Okay, Idris is present. Okay, I'm seeing you. Okay, so I'm gonna put you present. But what about Ouattara Idris Jr.?
Present, sir.
All right. How about Lai? Lai Kahela. Sar.
Present, sir.
Touré Nour. Touré Nour.
Present, sir.
All right. Touré Sheikh. I think he has written in the chat room. Touré Malaika.
Sir, I'm present.
All right. Perfect.
Present, sir.
Okay. So how about Mr. Lai? Lai Kaila. All right. So with that being said, I will see you on Wednesday. There will probably be a quiz on Wednesday. So be ready.
A quiz on what, sir? We covered a lot of things, sir.
Inverse of matrices. Let me write down in the chat room. Inverse of matrices. Inverse and multiplication of matrices.
Okay, sir.
Okay,
You can
sir.
add addition to.
Addition. But I assume that if you know how to do multiplication, that means you already know how to do addition.
Yes, but addition can bring us some points, sir, if we know. Okay.
So it's a quiz of the final. I will not.
You said? I haven't heard what you said.
It's about the quiz or the final.
No, it's about the quiz. The quiz on Wednesday.
Eh?
It's going to be on inverse of matrix. How to calculate. You have to know how to calculate the inverse of a matrix, and you have to know how to do multiplication of matrices.
Mm.
And then you will be fine for the quiz.
Okay.
Mhm.
Yes, sir,
Alright.
please.
Yes.
When you talk about multiplication, does it include partitioning?
No.
Okay, thank you, sir.
Yeah, it's like a normal type of multiplication. Because I'm pretty sure that some of you don't know how to do multiplication of matrix. I'm sure of that. So I want to check.
We'll know by then, sir.
Okay. All right. Sounds good. Sounds good. All right.
Goodbye, sir.
All right. Take care of yourself, and I'll see you on Wednesday.